In mathematics, a von Neumann algebra, a W** algebra, is a * algebra of bounded operators on a Hilbert space that is closed in the weak operator topology and contains the identity operator. It is a special type of C** algebra. Von Neumann algebra were originally introduced by John von Neumann, motivated by his study of single operators, group representations, ergodic theory and quantum mechanics. His double commutant theorem shows that the analytic definition is equivalent to a purely algebraic definition as an algebra of symmetries. Two basic examples of von Neumann algebras are as follows. The ring L infinity R of essentially bounded measurable functions on the real line is a commutative von Neumann algebra, which acts by pointwise multiplication on the Hilbert space L2 R of square integrable functions. The algebra B H of all bounded operators on a Hilbert space H is a von Neumann algebra, non-commutative if the Hilbert space has dimension at least 2. Von Neumann algebras were first studied by von Neumann, 1930. In 1929, he and Francis Murray developed the basic theory, under the original name of rings of operators, in a series of papers written in the 1930s and 1940s. F. J. Murray and J. von Neumann 1936. 1937. 1943. J. von Neumann 1938. 1940. 1943. 1949. Reprinted in the Collected Works of von Neumann. 1961. Introductory accounts of von Neumann algebras are given in the online notes of Jones, 2003, and Wasserman, 1991, and the books by Dixmeyer, 1981, Schwartz, 1967, Blackadar, 2005, and Sakai, 1971. The three-volume work by Takesaki, 1979, gives an encyclopedic account of the theory. The book by Cons, 1994, discusses more advanced topics. Definitions. There are three common ways to define von Neumann algebras. The first and most common way is to define them as weakly closed algebras of bounded operators on a Hilbert space containing the identity. In this definition, the weak operator topology can be replaced by many other common topologies, including the strong, ultra-strong or ultra-weak operator topologies. The * algebras of bounded operators that are closed in the norm topology are C** algebras. So in particular any von Neumann algebra is a C** algebra. The second definition is that a von Neumann algebra is a subset of the bounded operators closed under asterisk and equal to its double commutant, or equivalently the commutant of some subset closed under asterisk. The von Neumann double commutant theorem, von Neumann 1930, says that the first two definitions are equivalent. The first two definitions describe a von Neumann algebra concretely as a set of operators acting on some given Hilbert space. Sakai, 1971, showed that von Neumann algebras can also be defined abstractly as C** algebras that have a predual. In other words, the von Neumann algebra, considered as a Banach space, is the dual of some other Banach space called the predual. The predual of a von Neumann algebra is in fact unique up to isomorphism. Some authors use von Neumann algebra for the algebras together with a Hilbert space action, and W** algebra for the abstract concept. So a von Neumann algebra is a W** algebra together with a Hilbert space and a suitable faithful unital action on the Hilbert space. The concrete and abstract definitions of a von Neumann algebra are similar to the concrete and abstract definitions of a C** algebra, which can be defined either as norm-closed * algebras of operators on a Hilbert space, or as Banach asterisk algebra such that AA asterisk equals AA asterisk. Terminology. Some of the terminology in von Neumann algebra theory can be confusing, and the terms often have different meanings outside the subject. A factor is a von Neumann algebra with trivial center, i.e., a center consisting only of scalar operators. A finite von Neumann algebra is one which is the direct integral of finite factors, meaning the von Neumann algebra has a faithful normal, tracial state tau. M. CHTTP. Perso. ENS Leon. FR. Gaborii. Evenements. IHP trimester. IHP CIRM. Notes equals Cyril equals finite von Neumann. PDF. Similarly, properly infinite von Neumann algebras are the direct integral of properly infinite factors. A von Neumann algebra that acts on a separable Hilbert space is called separable. Note that such algebras are rarely separable in the norm topology. The von Neumann algebra generated by a set of bounded operators on a Hilbert space is the smallest von Neumann algebra containing all those operators. The tensile products of two von Neumann algebras acting on two Hilbert spaces is defined to be the von Neumann algebra generated by their algebraic tensile product. Considered as operators on the Hilbert space tensile products of the Hilbert spaces. By forgetting about the topology on a von Neumann algebra, we can consider it a unital asterisk algebra, or just a ring. Von Neumann algebras are semi-hereditary. Every finitely generated submodule of a projective module is itself projective. There have been several attempts to axiomatize the underlying rings of von Neumann algebras, including bare asterisk rings and or asterisk algebras. The asterisk algebra of affiliated operators of a finite von Neumann algebra is a von Neumann regular ring. The von Neumann algebra itself is in general not von Neumann regular. Commutative von Neumann algebras. The relationship between commutative von Neumann algebras and measure spaces is analogous to that between commutative C** algebras and locally compact Hausdorff spaces. Every commutative von Neumann algebra is isomorphic to L infinity x for some measure space x mu, and conversely, for every sigma finite measure space x. The asterisk algebra L infinity x is a von Neumann algebra. Due to this analogy, the theory of von Neumann algebras has been called non-commutative measure theory, while the theory of C** algebras is sometimes called non-commutative topology. Cons 1994. Projections. Operators E in a von Neumann algebra for which E equals E asterisk are called projections. They are exactly the operators which give an orthogonal projection of H onto some closed subspace. A subspace of the Hilbert space H is said to belong to the von Neumann algebra M if it is the image of some projection in M. This establishes a 1:1 correspondence between projections of M and subspaces that belong to M. Informally, these are the closed subspaces that can be described using elements of M, or that M knows about. It can be shown that the closure of the image of any operator in M and the kernel of any operator in M belongs to M. Also, the closure of the image under an operator of M of any subspace belonging to M also belongs to M. These results are a consequence of the polar decomposition. Comparison theory of projections. The basic theory of projections was worked out by Murray and von Neumann. 1936. Two subspaces belonging to M are called Murray von Neumann equivalent if there is a partial isometry mapping the first isomorphically onto the other that is an element of the von Neumann algebra. Informally, if M knows that the subspaces are isomorphic, this induces a natural equivalence relation on projections by defining E to be equivalent to F if the corresponding subspaces are equivalent. Or in other words, if there is a partial isometry of H that maps the image of E isometrically to The image of Fn is an element of the von Neumann algebra. Another way of stating this is that E is equivalent to F if E equals U asterisk and F equals U asterisk U for some partial isometry U in M. The equivalence relation tilde thus defined is additive in the following sense. Suppose E1 tilde F1 and E2 tilde F2. If E1 E2 and F1 F2, then E1 plus E2 tilde F1 plus F2. Additivity would not generally hold if one were to require unitary equivalence in the definition of tilde, i.e., if we say E is equivalent to F if U asterisk U equals F for some unitary U, the subspaces belonging to M are partially ordered by inclusion, and this induces a partial order of projections. There is also a natural partial order on the set of equivalence classes of projections, induced by the partial order of projections. If M is a factor, is a total order on equivalence classes of projections, described in the section on traces below. A projection, or subspace belonging to M, E is said to be a finite projection if there is no projection F less than E, meaning F E and F does not equal E, that is equivalent to E. For example, all finite-dimensional projections, or subspaces, are finite, since isometries between Hilbert spaces leave the dimension fixed. But the identity operator on an infinite-dimensional Hilbert space is not finite in the von Neumann algebra of all bounded operators on it, since it is isometrically isomorphic to a proper subset of itself. However, it is possible for infinite-dimensional subspaces to be finite. Orthogonal projections are non-commutative analogues of indicator functions in L-infinity. R. L-infinity, R, is the infinity closure of the subspace generated by the indicator functions. Similarly, a von Neumann algebra is generated by its projections. This is a consequence of the spectral theorem for self-adjoint operators. The projections of a finite factor form a continuous geometry. Factors. A von Neumann algebra N whose center consists only of multiples of the identity operator is called a factor. Von Neumann, 1949, showed that every von Neumann algebra on a separable Hilbert space is isomorphic to a direct integral of factors. This decomposition is essentially unique. Thus, the problem of classifying isomorphism classes of von Neumann algebras on separable Hilbert spaces can be reduced to that of classifying isomorphism classes of factors. Murray and von Neumann, 1936, showed that every factor has one of three types as described below. The type classification can be extended to von Neumann algebras that are not factors, and a von Neumann algebra is of type 10 if it can be decomposed as a direct integral of type 10 factors. For example, every commutative von Neumann algebra has type I1. Every von Neumann algebra can be written uniquely as a sum of von Neumann algebras of types I, 2, and 3. There are several other ways to divide factors into classes that are sometimes used. A factor is called discrete, or occasionally tame, if it has type 1, and continuous, or occasionally wild, if it has type 2 or 3. A factor is called semi-finite if it has type 1 or 2, and purely infinite if it has type 3. A factor is called finite if the projection 1 is finite and properly infinite otherwise. Factors of types I and 2 may be either finite or properly infinite, but factors of type 3 are always properly infinite. Type 1 factors. A factor is said to be of type 1 if there is a minimal projection E does not equal 0, i.e., a projection E such that there is no other projection F with 0 less than F less than E. Any factor of type 1 is isomorphic to the von Neumann algebra of all bounded operators on some Hilbert space. Since there is one Hilbert space for every cardinal number, isomorphism classes of factors of type 1 correspond exactly to the cardinal numbers. Since many authors consider von Neumann algebras only on separable Hilbert spaces, it is customary to call the bounded operators on a Hilbert space of finite dimension n a factor of type n, and the bounded operators on a separable infinite-dimensional Hilbert space a factor of type 1 infinity. Type 2 factors. A factor is said to be of type 2 if there are no minimal projections but there are non-zero finite projections. This implies that every projection E can be halved, in the sense that there are two projections F and G that are Murray-von Neumann equivalent and satisfy E equals F plus G. If the identity operator in a type 2 factor is finite, the factor is said to be of type 2-1. Otherwise, it is said to be of type 2 infinity. The best understood factors of type 2 are the hyperfinite type 2-1 factor and the hyperfinite type 2 infinity factor, found by Murray and von Neumann, 1936. These are the unique hyperfinite factors of types I1 and 2 infinity. There are an uncountable number of other factors of these types that are the subject of intensive study. Murray and von Neumann, 1937, proved the fundamental result that a factor of type 2-1 has a unique finite tracial state, and the set of traces of projections is O1. A factor of type 2 infinity has a semi-finite trace, unique up to rescaling, and the set of traces of projections is 0. Infinity. The set of real numbers lambda such that there is an automorphism rescaling the trace by a factor of lambda is called the fundamental group of the type 2 infinity factor. The tensile products of a factor of type 2-1 and an infinite type 1 factor has type 2 infinity. And conversely, any factor of type 2 infinity can be constructed like this. The fundamental group of a type 2-1 factor is defined to be the fundamental group of its tensor product with the infinite separable factor of type 1. For many years it was an open problem to find a type 2 factor whose fundamental group was not the group of positive reals. But Kantz then showed that the von Neumann group algebra of a countable discrete group with Cardan's property T. The trivial representation is isolated in the dual space, such as SL 3 Z has a countable fundamental group. Subsequently, Soren-Popper showed that the fundamental group can be trivial for certain groups, including the semi-direct product of Z2 by SL 2 Z. An example of a type 2-1 factor is the von Neumann group algebra of a countable infinite discrete group such that every non-trivial conjugacy class is infinite. McDuff, 1969, found an uncountable family of such groups with non-isomorphic von Neumann group algebras, thus showing the existence of uncountably many different separable type 2-1 factors. Type 3 factors. Lastly, type 3 factors are factors that do not contain any non-zero finite projections at all. In their first paper, Murray and von Neumann, 1936, were unable to decide whether or not they existed. The first examples were later found by von Neumann, 1940. Since the identity operator is always infinite in those factors, they were sometimes called type 3 infinity in the past. But recently that notation has been superseded by the notation 3 lambda, where lambda is a real number in the interval O1. More precisely, if the Kantz spectrum of its modular group is 1, then the factor is of type 3 0. If the Kantz spectrum is all integral powers of lambda for 0 less than lambda less than 1, then the type is 3 lambda. And if the Kantz spectrum is all positive reals, then the type is III1. The Kantz spectrum is a closed subgroup of the positive reals. So these are the only possibilities. The only trace on type 3 factors takes value infinity on all non-zero positive elements, and any two non-zero projections are equivalent. At one time type 3 factors were considered to be intractable objects, but Tomita-Takesaki theory has led to a good structural theory. In particular, any type 3 factor can be written in a canonical way as the cross product of a type 2 infinity factor and the real numbers. The predual. Any von Neumann algebra M has a predual M, which is the Banach space of all ultra-weakly continuous linear functionals on M. As the name suggests, M is, as a Banach space, the dual of its predual. The predual is unique in the sense that any other Banach space whose dual is M is canonically isomorphic to M. Sakai, 1971, showed that the existence of a predual characterizes von Neumann algebras among C** algebras. The definition of the predual given above seems to depend on the choice of Hilbert space that M acts on, as this determines the ultra-weak topology. However, the predual can also be defined without using the Hilbert space that M acts on, by defining it to be the space generated by all positive normal linear functionals on M. Here, normal means that it preserves suprema when applied to increasing nets of self-adjoint operators, or equivalently to increasing sequences of projections. The predual M is a closed subspace of the dual M**, which consists of all norm-continuous linear functionals on M, but is generally smaller. The proof that M is usually not the same as M** is non-constructive and uses the axiom of choice in an essential way. It is very hard to exhibit explicit elements of M** that are not in M. For example, exotic positive linear forms on the von Neumann algebra L infinity Z are given by Fourier ultrafilters. They correspond to exotic asterisk homomorphisms into C and describe the Stonecheck compactification of Z. Examples: the predual of the von Neumann algebra L infinity R of essentially bounded functions on R is the Banach space L1 R of integrable functions. The dual of L infinity R is strictly larger than L1 R. For example, a functional on L infinity R that extends the Dirac measure delta 0 on the closed subspace of bounded continuous functions COB R cannot be represented as a function in L1 R. The predual of the von Neumann algebra B H of bounded operators on a Hilbert space H is the Banach space of all trace class operators with the trace norm A equals TR. A. The Banach space of trace class operators is itself the dual of the C** algebra of compact operators, which is not a von Neumann algebra. Weights, states, and traces. Weights and their special cases, states and traces, are discussed in detail in Takesaki, 1979. A weight omega on a von Neumann algebra is a linear map from the set of positive elements, those of the form A** A 2, 0, infinity. A positive linear functional is a weight with omega 1, finite, or rather the extension of omega to the whole algebra by linearity. A state is a weight with omega 1 equals 1. A trace is a weight with omega A** equals omega A** for all A. A traceal state is a trace with omega 1 equals 1. Any factor has a trace such that the trace of a non-zero projection is non-zero and the trace of a projection is infinite if and only if the projection is infinite. Such a trace is unique up to rescaling. For factors that are separable or finite, two projections are equivalent if and only if they have the same trace. The type of a factor can be read off from the possible values of this trace as follows. Type in 0, x, 2x, nx for some positive x, usually normalized to be 1, n1. Type 1 infinity, 0, x, 2x, infinity for some positive x, usually normalized to be 1. Type 2 1, 0, x, for some positive x, usually normalized to be 1. Type 2 infinity, 0, infinity. Type 3, 0, infinity. If a von Neumann algebra acts on a Hilbert space containing a norm 1 vector v, then the functional a av v is a normal state. This construction can be reversed to give an action on a Hilbert space from a normal state. This is the GNS construction for normal states. Modules over a factor. Given an abstract separable factor, one can ask for a classification of its modules, meaning the separable Hilbert spaces that it acts on. The answer is given as follows. Every such module H can be given an m-dimension dim H, not its dimension as a complex vector space, such that modules are isomorphic if and only if they have the same m-dimension. The m-dimension is additive, and a module is isomorphic to a subspace of another module if and only if it has smaller or equal m-dimension. A module is called standard if it has a cyclic separating vector. Each factor has a standard representation, which is unique up to isomorphism. The standard representation has an antilinear involution J such that Jmj equals m. For finite factors, the standard module is given by the GNS construction applied to the unique normal tracial state, and the m-dimension is normalized so that the standard module has m-dimension 1, while for infinite factors the standard module is the module with m-dimension equal to infinity. The possible m-dimensions of modules are given as follows. Type in n finite. The m-dimension can be any of 0, n, 1, n, 2, n, 3, n, infinity. The standard module has m-dimension 1. In complex dimension n2. Type 1 infinity. The m-dimension can be any of 0, 1, 2, 3, infinity. The standard representation of B H is HH. Its m-dimension is infinity. Type 2 1. The m-dimension can be anything in 0, infinity. It is normalized so that the standard module has m-dimension 1. The m-dimension is also called the coupling constant of the module H. Type 2 infinity. The m-dimension can be anything in 0, infinity. There is in general no canonical way to normalize it. The factor may have outer automorphisms multiplying the m-dimension by constants. The standard representation is the one with m-dimension infinity. Type 3. The m-dimension can be 0 or infinity. Any two non-zero modules are isomorphic, and all non-zero modules are standard. Amenable von Neumann algebras. Cons. 1976. And others proved that the following conditions on a von Neumann algebra M on a separable Hilbert space H are all equivalent. M is hyperfinite or AFD or approximately finite dimensional or approximately finite. This means the algebra contains an ascending sequence of finite dimensional subalgebras with dense union. Warning. Some authors use hyperfinite to mean AFD and finite. M is amenable. This means that the derivations of M with values in a normal dual-Banach bimodule are all inner. M has Schwarz's property P. For any bounded operator T on H, the weak operator closed convex hull of the elements UTU** contains an element commuting with M. M is semi-discrete. This means the identity map from M to M is a weak pointwise limit of completely positive maps of finite rank. M has property at the Hakeda-Tomoyama extension property. This means that there is a projection of norm 1 from bounded operators on H to M. M is injective. Any completely positive linear map from any self-adjoint closed subspace containing one of any unital C** algebra A to M can be extended to a completely positive map from A to M. There is no generally accepted term for the class of algebras above. Kant has suggested that amenable should be the standard term. The amenable factors have been classified There is a unique one of each of the types in I infinity, II1, 2 infinity, 3 lambda, for 0 less than lambda 1. And the ones of type 30 correspond to certain ergodic flows. For type 30, calling this a classification is a little misleading, as it is known that there is no easy way to classify the corresponding ergodic flows. The ones of type 1 and II1 were classified by Murray and von Neumann, 1943, and the remaining ones were classified by Cons, 1976. Except for the type 3-1 case, which was completed by Hagerup. All amenable factors can be constructed using the group measure space construction of Murray and von Neumann for a single ergodic transformation. In fact, they are precisely the factors arising as crossed products by free ergodic actions of Z or Z, NZ on abelian von Neumann algebras L infinity X. Type 1 factors occur when the measure space X is atomic and the action transitive. When X is diffuse or non-atomic, it is equivalent to O1 as a measure space. Type 2 factors occur when X admits an equivalent finite II1 or infinite 2 infinity measure, invariant under an action of Z. Type 3 factors occur in the remaining cases where there is no invariant measure, but only an invariant measure class. These factors are called Krieger factors. Tensile products of von Neumann algebras. The Hilbert space tensile products of two Hilbert spaces is the completion of their algebraic tensor product. One can define a tensor product of von Neumann algebras. A completion of the algebraic tensor products of the algebras considered as rings, which is again a von Neumann algebra, and act on the tensor products of the corresponding Hilbert spaces. The tensor products of two finite algebras is finite, and the tensor product of an infinite algebra and a non-zero algebra is infinite. The type of the tensor products of two von Neumann algebras, I, 2, or 3, is the maximum of their types. The commutation theorem for tensor products states that m n single quote equals m single quote n single quote display style m o times n caret prime equals m caret prime o times n caret prime, closing curly bracket, where m denotes the commutant of m. The tensor products of an infinite number of von Neumann algebras, if done naively, is usually a ridiculously large non-separable algebra. Instead, von Neumann, 1938, showed that one should choose a state on each of the von Neumann algebras. Use this to define a state on the algebraic tensor product, which can be used to produce a Hilbert space in a reasonably small von Neumann algebra. Araki and Woods, 1968, studied the case where all the factors are finite matrix algebras. These factors are called Araki-Woods factors or ITPFI factors. ITPFI stands for infinite tensor products of finite type 1 factors. The type of the infinite tensor product can vary dramatically as the states are changed. For example, the infinite tensor products of an infinite number of type I2 factors can have any type depending on the choice of states. In particular, Powers, 1967, found an uncountable family of non-isomorphic hyperfinite type 3 lambda factors for 0 less than lambda less than 1, called Powers factors. By taking an infinite tensor products of type I2 factors, each with the state given by x, t, r, 1, lambda, plus, 1, 0, 0, lambda, lambda, plus, 1, x, display style x, mapsto, room, tr, begin, p matrix, 1, over, lambda plus 1, and 0, 0, and, lambda, over, lambda plus 1, end, p matrix, x, closing curly bracket. All hyperfinite von Neumann algebras not of type 3.0 are isomorphic to Araki-Woods factors. But there are uncountably many of type 3.0 that are not. Bimodules and subfactors. A bimodule, or correspondence, is a Hilbert space H with module actions of two commuting von Neumann algebras. Bimodules have a much richer structure than that of modules. Any bimodule over two factors always gives a subfactor, since one of the factors is always contained in the commutant of the other. There is also a subtle relative tensor products operation due to cons on bimodules. The theory of subfactors, initiated by Vaughan Jones, reconciles these two seemingly different points of view. Bimodules are also important for the von Neumann group algebra M of a discrete group gamma. Indeed, if B is any unitary representation of gamma, then, regarding gamma as the diagonal subgroup of gamma times gamma, the corresponding induced representation on L2, gamma, V, is naturally a bimodule for two commuting copies of M. Important representation theoretic properties of gamma can be formulated entirely in terms of bimodules and therefore make sense for the von Neumann algebra itself. For example, Combs and Jones gave a definition of an analog of Kazhdan's property T for von Neumann algebras in this way. Non-amenable factors. Von Neumann algebras of type 1 are always amenable. But for the other types there are an uncountable number of different non-amenable factors, which seem very hard to classify, or even distinguish from each other. Nevertheless, Voiculescu has shown that the class of non-amenable factors coming from the group measure space construction is disjoint from the class coming from group von Neumann algebras of free groups. Later, Narutaka Ozawa proved that group von Neumann algebras of hyperbolic groups yield prime-type II1 factors, i.e., ones that cannot be factored as tensor products of type 2-1 factors, a result first proved by Leeming G for free group factors using Voiculescu's free entropy. Popper's work on fundamental groups of non-amenable factors represents another significant advance. The theory of factors beyond the hyperfinite is rapidly expanding at present, with many new and surprising results. It has close links with rigidity phenomena in geometric group theory and ergodic theory. Examples: the essentially bounded functions on a sigma finite measure space form a commutative type I1 von Neumann algebra acting on the L2 functions. For certain non-sigma finite measure spaces, usually considered pathological, L∞, X, is not a von Neumann algebra. For example, the sigma algebra of measurable sets might be the countable-co-countable algebra on an uncountable set. The bounded operators on any Hilbert space form a von Neumann algebra. Indeed, a factor of type 1. If we have any unitary representation of a group G on a Hilbert space H, then the bounded operators commuting with G form a von Neumann algebra G, whose projections correspond exactly to the closed subspaces of H invariant under G. Equivalent subrepresentations correspond to equivalent projections in G. The double commutant G of G is also a von Neumann algebra. The von Neumann group algebra of a discrete group G is the algebra of all bounded operators on H equals L2 G, commuting with the action of G on H through right multiplication. One can show that this is the von Neumann algebra generated by the operators corresponding to multiplication from the left with an element GG. It is a factor of type 2-1. If every non-trivial conjugacy class of G is infinite, for example, a non-abelian free group, and is the hyperfinite factor of type 2-1 if in addition G is a union of finite subgroups, for example, the group of all permutations of the integers fixing all but a finite number of elements, the tensor products of two von Neumann algebras, or of a countable number with states. is a von Neumann algebra as described in the section above. The crossed product of a von Neumann algebra by a discrete, or more generally locally compact, group can be defined, and is a von Neumann algebra. Special cases are the group measure space construction of Murray and von Neumann and Krieger factors. The von Neumann algebras of a measurable equivalence relation and a measurable groupoid can be defined. These examples generalize von Neumann group algebras and the group measure space construction. Applications. Von Neumann algebras have found applications in diverse areas of mathematics like knot theory, statistical mechanics, quantum field theory, local quantum physics, free probability, non-commutative geometry, representation theory, geometry, and probability. For instance, C-star algebra provides an alternative axiomatization to probability theory. In this case, the method goes by the name of John von Neumann-Siegel construction. This is analogous to the two approaches to measure and integration, where one has the choice to construct measures of sets first and define integrals later, or construct integrals first and define set measures as integrals of characteristic functions. Araki, H. Woods, E. J. 1968. A classification of factors. PUBL. Res. Inst. Math. Sci. Sir. A. 4. 1. 51-130. DOI. 10.2977 Prims 1,195,195,263 MRO 244773. Blackadar. B. 2005. Operator algebras. Springer. ISBN 3-540-28486-9. Corrected manuscript. PDF. 2013. Cons. A. 1976. Classification of injective factors. Annals of Mathematics. 2nd Series. 104. 1. 73-115. DOI. 10.2307 1,971,057. JSTOR 1,971,057. Cons. A. 1994. Non-commutative geometry. PDF. Academic Press. ISBN 0-12-185860-X. Dixmeyer, J. 1981. Von Neumann algebras. ISBN 0-444-86308-7. A translation of Dixmeyer, J. 1957. Les algebras d'opérateurs dans l'espace Hilbertien. Algebras de von Neumann. Gauthier Villas. The first book about von Neumann algebras. Jones. V. F. R. 2003. Von Neumann algebras. PDF. Incomplete notes from a course. Kostecki. R. P. 2013. W** algebras and non-commutative integration. Arxiv. 1307.4818. Macduff. Doucet. 1969. Uncountably many II1 factors. Annals of Mathematics. 2nd Series. 90. 2. 372-377. DOI. 10.2307 1,970,730. JSTOR 1,970,730. Murray, F. J. The Rings of Operators Papers. The Legacy of John von Neumann. Hempstead, N.Y. 1988. Proc. Sympos. Pure Math. 50. Providence. Re. Amar. Math. Soc. pp. 57-60. ISBN 0-8218-4219-6. A historical account of the discovery of von Neumann algebras. Murray, F. J. Von Neumann, J. 1936. On rings of operators. Annals of Mathematics. 2nd series. 37. 1. 116 to 229. DOI. 10.2307 1,968,693. JSTOR 1,968,693. This paper gives the basic properties and the division into types I, II, and III, and in particular finds factors not of type 1. Murray, F. J. von Neumann, J. 1937. On rings of operators 2. Trans. A. Ma. Math. Soc. American Mathematical Society. 41. 2. 208 to 248. DOI. 10.2307 1,989,620. JSTOR 1,989,620. This is a continuation of the previous paper that studies properties of the trace of a factor. Murray, F. J. von Neumann, J. 1943. On rings of operators IV. Annals of Mathematics. 2nd series. 44. 4. 716 to 808. DOI. 10.2307 1,969,107. JSTOR 1,969,107. This studies when factors are isomorphic, and in particular shows that all approximately finite factors of type 2-1 are isomorphic. Powers, Robert T. 1967. Representations of uniformly hyperfinite algebras and their associated von Neumann rings. Annals of Mathematics. 2nd series. 86. 1. 138 to 171. DOI. 10.2307 1,970,364. JSTOR 1,970,364. Sakai, S. 1971. C** Algebras and W** Algebras. Springer. ISBN 3-540-63633-1. Schwartz, Jacob. 1967. W** Algebras. ISBN 0-677-00670-5. Stern, A. I. 2001. Von Neumann Algebra. In Hayes-Winkel. Muschiel. Encyclopedia of Mathematics. Springer. ISBN 978-1-55608-010-4. Takesaki, M. 1979. Theory of operator algebras I. 2. 3. ISBN 3-544-224-8-X. Von Neumann, J. 1930. Zur Algebra der Funktionaloperation und Theorie der normalen Operatoren. Math. An. 102. 1. 370-427. DOI. 10.1007, BFO 1782352. The original paper on von Neumann algebras. Von Neumann, J. 1936. On a certain topology for rings of operators. Annals of Mathematics. 2nd series. 37. 1. 111 to 115. DOI. 10.2307 1,968,690. JSTOR 1,968,692. This defines the ultra-strong topology. Von Neumann, J. 1938. On infinite direct products. Compose. Math. 6. 1 to 77. This discusses infinite tensor products of Hilbert spaces and the algebras acting on them. Von Neumann, J. 1940. On rings of operators. 3. Annals of Mathematics. 2nd Series. 41. 1. 94 to 161. DOI. 10.2307 1,968,823. JSTOR 1,968,823. This shows the existence of factors of type 3. Von Neumann, J. 1943. On some algebraical properties of operator rings. Annals of Mathematics. 2nd Series. 44. 4. 709 to 715. DOI. 10.2307 1,969,106. JSTOR 1,969,106. This shows that some apparently topological properties in von Neumann algebras can be defined purely algebraically. Von Neumann, J. 1949. On rings of operators. Reduction theory. Annals of Mathematics. 2nd Series. 50. 2. 401 to 485. DOI. 10.2307 1,969,463. JSTOR 1,969,463. This discusses how to write a von Neumann algebra as a sum or integral of factors. Von Neumann, John. 1961. Taub, A. H. ed. Collected Works. Volume 3. Rings of Operators. N.Y. Pergamon Press. Reprints von Neumann's papers on von Neumann algebras. Wasserman, A. J. 1991. Operators on Hilbert space.